Hello everyone. So this is a part 2 of this video on fashion neural network with FashionMNIST dataset. In the part 1 we did project how to create the project directory, how to download the dataset, how to create data loader, and we saw some sample images from using the data loader. So in this lesson we'll create a neural network. So neural network is nothing but a class. We'll create a class and we will name it as a neural network. So this is a neural network and it will be a base class of NN.module. We can run our previous code first. Okay, so this is the neural network class, and in this neural network we need basically two functions. One, to initialize all of the variables that we will be using, that will be our layers, and the second will be the forward function. And in the initialization class we will use first we need to call the NN.modules initialization function with neural network, and this passing the self dot init. Okay, so this is our neural network. Super. And now we'll write more functions here, more statements here. What to do? We'll declare more variables here later on, and then we need to define a forward function. Forward, and it will take the instance of the class, which will be our model later on, and an image x, and we'll write the forward pass statements here. Okay, so before we write the statements we will be using two of the methods from the torch library. Our first will be the nn.flatten. So for example, we have the image. So far let's create in the part 1 we have seen that this data loader or train data loader or test data loader creates a batch of the images of size 64 by 1 28 28 of the train data loader, and we have seen this using the next of ITER and then train data loader. Okay, so this is our capital X and Y. It returns data and its label, and we see this image x dot shape. This is 64 128 128. So now what we want to do is, if we want this is the batch that which is 64 1 20 20. In order to do the neural network we need to flatten these numbers. So this is a matrix so far 28 by 28. So what we need is 28 into 28, so basically 784 numbers. So consider the neural network as a Microsoft Excel table in which we have the images on the row wise, but there are 784 columns for each image and there are 64 rows. So we need to convert this from shape 64 1 20 28 to 64 28 28. And even if it's for a colored image, say if the colored image is 64 3 28 28, then what we'll do is we will create 3 into 28 by 20, so it will be 64, and then it will be having the 2352 columns. So all of the features are columns and the batch is in the terms of number of rows. So what we want here is 128 28, and this functionality or this conversion can be used. We can use the nn.flatten to convert to flatten these nodes or features. nn.flatten. So this is nn.flatten. So if we pass x here, and now the x will be, and now if I say what is the x dot shape, so this is now 64 by 7084. So this is what we want to do in the forward class, in the forward pass, that we will first, if this x currently initially x will be of this shape 64, 128, 28, and when we'll flatten, then it will become 784, 1784. So this is that's our first task. And next layer, so what I can do is we can write it like this one. So this is nn dot flatten, and we can create a variable first here, that our self dot flatten is equal to nn dot flatten, and then we can call this self dot flatten on the x. So we can say x is equal to self dot flatten and x. Okay, so first part is done, that we have created we have flattened the layer, so we have the input layer ready. Next, after flattening, so now is the we need to create layer by layer. Our first layer will be, for example, we have 784 features from the input layer, or we have 784 neurons at the input layer, and maybe we want to convert this to 512 neurons. So in our output, what we want from the layer 1 is 64, 512. So we have 784 and we want to reduce the features. Sometimes we want to increase, sometimes we want to reduce. So we're not it depends on the network architecture, how you want to create, but let's say that I want to reduce it to 512, and the idea is to gradually reduce these layers, using these layers to reduce these nodes, and finally we will be at the final layer, we will having a 10 output nodes. Okay, so now how to reduce these features? Basically, we have an Excel sheet. For example, there are 64 rows and 784 columns, and we want to convert this to 64 into 512. And if you know the matrix multiplication, you need to create a matrix of 784 into 512. So if you have a matrix of 64 into 784, let's say you have a matrix of size 64 into 784, and if I multiply with a matrix called 784 into 512, and this matrix multiplication will give me a matrix called with shape 64 into 512. So this is what the neural network's first layer will do, and from where we will get these numbers of this matrix. These are the weights. So we will create some matrix of this shape, and then we'll multiply this one, and then we'll get this one. Okay, so we have a function called here nn dot linear to do this task. So this is an n dot linear. So when we pass this, in this one we need to write it, that what matrix we want. For example, we already have 784, so we'll write here that 784 here, and then we want to convert into 512. So this is our the nn dot linear, and now we'll pass the x to this one, and now we'll see x is equal to this one. So we have converted that. Now we'll see what is x dot shape. Okay, so this has become 64 into 512. Okay, so let me write it again, what we are going to do. So we have this idea. So we got the image from train data loader. We will flatten these images, and then we will apply the linear we will apply this linear transformation, and now our shape will be 64 into 512. Okay. So after this one, we'll apply a value function, activation function. So these numbers, if you see these numbers, will have some negative number and there may be some positive numbers. So this is a positive number, there are some negative numbers. So ReLU will only keep the positive numbers, and basically ReLU is just 0 and x. So it will find out maximum of these two. Yes, if we pass this one, so it will give you, if the number is x, if it is a positive, then it will keep that number as it is. Otherwise, if it is a negative number, then it will return the 0 number. Okay, so that's our activation function. Okay, so now what we'll do is we'll write here that we have x is equal to, we have flattened, and now we'll create our layer 1. Okay, in order to create layer 1, so we can just call a variable called layer 1. We can just name it layer 1, and we can call nn dot linear. And in the nn dot linear, since we are going to convert 28 by 20, which is 784, to 512, so we'll write it here that we are going to have this 512. Okay, and now we will need another layer called layer 2. So layer 2 will be, layer 2 will convert that 512 to maybe 512. Same, we can just have same number. So it will convert again 512 to 512, and we can have another layer called layer 3, and we can say that it will convert to 512 to 10, and 10 are our number of classes. And all of these layers by default has bias is equal to true. Even if you will not write, then bias is equal to true will be there. And you can check it also. So bias is true. So bias is nothing but when we have this transformation, which is y is equal to mx plus c, so c is called a bias. So what does it when you say that nn dot linear is doing? So basically we have, for example, let's say we have three features x1, x2, x3, and we are going to convert to two features. Y1 is equal to mx plus c, means we can have w11 x1 plus w12 into x2 and plus w13 into x3 and plus c b bias 1 b1. So what happened in this one is, so if we have only 3 elements, we have 784, so it will go like this one: x1, x2, x3, 784, and this is your matrix, which we are calling it from 784 by 500 in case we want 512. But if you want just 2, then it will be y1 and y2 only. Okay, so at this one b1 is the bias, so by default it will always be there. So if you say bias is false, then b1 will not be. So this will affect our number of parameters, that how much we want to train. Okay. And similarly, if we want to convert to 3 to 2, then we just have to this one y2, and this will be 2-1. So this is 2-2, and this is 2-3, and this is the back 2. So in this one we have converted from 3 to 2 numbers, but here we are converting from 784 to 512. So we'll have y1, y2, y3 up to 512, but w1, w2, w13, w1 784. Similarly, x1, x2, x3 will be 784, and plus there will be bias. So when we want to count the number of parameters, if our bias is true, then the number of parameters will be 784 into 512 into number of bias, and number of biases will be how much? How many y1, y2 have. So since y1 will be 512, so we'll add these 500. So we'll count all of these number of parameters soon. Okay, so this is what we are going to do. And lastly, we need some activation function here, and we can call this as self.relu is equal to nn.relu. So this is our activation function that we will be using. And now we have flattened. So we have flattened means that we have now 784 elements in this one. Okay, so what we're going to do here now is that we will convert these 784 numbers to 512. And how can we convert to the 512? So we have this already defined this layer. So we will call this layer self.layer1, and we'll pass this x here. So now this is 512. And we need to pass use the ReLU function, because if we will not use the activation function, so then there is no point of having all of the layers. So it is just single layer without activation function. Okay. So any activation function is important. So we have just, and how to use this one now. So we have self dot value, so we'll pass this x to the self dot value, and this x will give us self dot value. So we started here with the 784 elements here, or 28 by 28, and this will give us 512, because this linear one gives us 512. And we will repeat this set for the second layer also. So our second layer will give us 512, and value will give same, because value doesn't change the number of parameter, it just gives you the maximum of 0 and positive numbers x if it is okay. So we have this one. Next, last is the output layer. So for the output layer, this one will give us this, we want here number, output will be 10, and we call it 3x, and this. So these are called the logics. Okay, and now we can return x. So this is our neural network basically. So we have we will first flatten the layer. So this is the input layer, which has 784 numbers coming from the image, all the pixel values. And then we have layer 1 that converts 784 to 512, and then activate some of the neurons. And then we have another layer which keeps 512 and activates again some of the neurons. And then we have layer 3 which gives us the 10 logics. So this is our neural network. So now we'll count the number of parameters. So in order to count the number of parameters, first we can see the we can call a function called PyTorch model summary. So I have this. I have already included here the library that you can use, PyTorch model summary. So this is the library we will use, and we will call this summary function from this one. And let's say we want to store the table. So we have a parameter table, and we'll count this parameter, count the number of parameters soon manually also. And first, let's see that how does this summary table give us. So in the summary, what we want to do is we need to pass the model first, and before that we need to create a model. So model is equal to nothing, but you need to just call this class neural network. So this is our neural network, and we can print here also, print model. So this is the model that we have pattern layer, we have linear 1, linear 2, linear 3, and activation function. And you can see in all of these layers it's saying the bias is equal to true, although we have just set bias is true for the layer 1 only. By default it is always true. Okay, so we need to pass this model here, and then what we need to pass is we need to give some image shape here, because it is expecting a shape of 28 by 28. So what we will do is we'll create one, maybe just element with zeros only, torch dot, you can just create any torch dot 1, torch dot 0, any data with one batch, one channel, 28 by 28. So this is our expectation, torch dot 0, 0. And then we will see, we will just say show input is equal to true, so that we get what is input also. In our table, this input will be shown. Okay, so and then we can print this table. Print. Okay, so this is the input shape. So we give them the this is our input shape to the flatten layer 1, 1, 20, 20. There are no parameters in the flatten. In the linear 2, it will receive 784, and there are parameters 401920. Now how these parameters are coming from 401920 at linear 2. So this is our first hidden layer. So what it does is that we have in the first layer we have 784 in numbers, and these are converted to 512. So we have seen just now. So it will be 784 multiplied by 500. So number of parameters means number of elements in that matrix. So this will be 401, 408. But this is still higher than this one. This is because we have said bias is equal to true. So we need to add the 512 plus. So it will be 401920. Similarly, at the layer 2 and layer 3, we can count these numbers there. So okay, so let's start with this one again. So we have an initial layer which is 1 into 784, and what we want from the output is 512. So this is what we want, and in order to achieve this objective, so we need to multiply this number with 784 and by 512, then only we will get this. So this is our task of our first hidden layer. So this is our input layer, which is the 1 into 784, and this is what we want from our output from the hidden layer. So it needs to multiply with this one, but it doesn't multiply by just like these numbers, but it also will add a bias here also, and bias is nothing but 1 into 512. So this is the transformation or mathematical function that is implemented when bias is equal to true. So when bias is false, so these numbers will not be added, and we can check it here also. So let's say that I'm saying here bias is equal to false for this layer only. Okay, so I run this one, and this is bias is equal to false, and now if I'll see, it will not be 401920, it is 401408, and we can see it here, and 401408 means only 784 multiplied by 512. So this is 401,408, exactly same. Okay, so although the matrix is this one that needs to be multiplied, bias will be added. Okay, so we need to keep it as true, because why we want to keep the bias as true? Because if there is no bias, then it means that our function is like this one. The y1 is equal to some w11 x1 plus w12 x2 and plus w13 x3. And if there is no bias, means it is zero, bias is zero, then at origin, for example, if x1 x2 x3 is 0, then y is always 0. So this will estimate only functions which are true, which are tied to the origin. So in case you want to generalize it, which may be true for some of the problems, but not for all of the problems, and not for many problems. So it's always good that we keep the bias, and if bias is to be 0, then neural network will estimate the value as a 0. So we don't have to worry about that. So that's why we need to keep the bias as a true. Okay, so this is the function number of parameters in our first layer. I'll just run it again. So we have bias is equal to true now, and now these are what number of parameters, 401920, and 401920 is coming from multiply this and this is, so these are the number of parameters that will be estimated during the training. And next, in the next layer, then the value, it will still remain same. If we will give 512, it will give us 512. So value does nothing other than activating the positive value neurons only, and if it is negative, then it will keep at a 0. Okay, and in the layer 2, what we have said is it will take the input as 512, and it will give us the output also 512. So in order to do that, it will multiply with the matrix of 512 by 512, and will add this one also. So in case we want to achieve this function, number of parameters in this will be 784 into 512 plus 512. So these are the number of parameters in this one, and if we want to achieve this objective, then we need 512 into 512 plus 512. So this is the number of 262656. You can see here 262656. And at the last layer, which is our output layer, so what we want is it will receive this number, a matrix of 1 into 512, and it gives us the output of 1 into 10. So now we want 10 output. For example, here we said 512 to 10. So it receives 512, but it gives us 10. So what we need to do is we need to multiply with the matrix called 512 and then 10. So it will give us 10, but we also, since the bias is true, so our this will be 1 into 10. So these are the number of parameters in this one. So if we want to compute the number of parameters, so we'll say 512 into 10 plus 10. 5130, and we can see it here 5, and adding all of these numbers will be 669706. So these are the trainable parameters. So if you don't want to train some of the parameters, we can freeze those parameters, and then it will show in the parameters but not in the trainable parameters. So far we have not done that. We will do that in our future lessons when we will do the convolution neural network, wherein we will use some transfer learning. We know that initial layers are not to be trained because these are already trained, to save our time, save our memory and everything. So we freeze those parameters so that we don't need training for those parameters. But so far we have our total parameters are all to be trained. So this is all about the neural network. And if you want to see these parameters also, you can write a function here that if you want to count, for example, number of parameters. This is we have all counted manually, and this is we have a table here that accounts. But let's say we want to write a function here, or maybe just code here that how to count these parameters. So we can start with parameters. We can do parameters is equal to, we can initialize the parameters equal to 0, and we can write a function glue here for p in model dot parameters. So we already have a model and dot parameters. So all of the parameters can be accessed using the model dot parameters. So p is a model dot parameters, and what we want to do is parameters parameters plus equal to. So when we say plus equal to, and we can find out from p is a model of parameter, we can find out use p dot number of elements. You can call this one p is again a tensor which has a shape of 784 512 plus this thing. So we can just need to call this p dot number of elements, and then we can print these number of elements. 669706. So we can say 669706. So this is also another way to count the number of parameters. And if you want to see the number of parameters, you can also use the list comprehension. You can just say that you want parameters is equal to p dot number of elements for p in model dot parameter. So we can print these parameters here. So these are the number of parameters it's showing, 4010, and then bias it shows differently, and 5120 and 10. So these are the number of parameters, and then if you add these parameters, just write it as a print parameters, and then print sum of the parameters. Okay, 669006. So this is exactly the same. Okay, so one more thing that we generally should do is, when we are counting these parameters, we need to use if statement that we need to count only the trainable parameters. But how to get these are the total parameters. But so far in this case it will be same, but in future lesson you need to call this one, in which we will say if p dot, if it is a trainable parameter, then its required gradient will be true. So it just requires grad. If p dot requires grad, then we add, otherwise we don't add it to this one. And similarly we can also use this p dot requires grad in our here also for p in p, but only when if p dot requires grad is true. So it won't have no effect right now, but in future lessons we need to use this one. So this is all about neural network, and in that next and last lesson for this one, the neural network is a FashionMNIST dataset. What we'll do is we will now We'll train this dataset using this neural network, and we'll see how is the accuracy of this model. We'll use the 10 epochs for this one, using batch size 10 and some learning rate 0.001, and see how this neural network performs. And if it doesn't perform, we may need to add layers into this one, or we may need to use maybe different activation function. We need to change learning rate, we will need to change bias. So these are the things that we always need to explain. Okay, thank you very much.